All righty, good morning, everyone. So happy Friday. It's supposed to be another hot day today, at least as far as this year is concerned. So good. So let me read in and then let's go ahead and remind ourselves what we talked about yesterday. Well, first there's an announcement. So I did post the extra credit for exam number 4 on Blackboard this morning. So that is finally there. I think I was said I was going to do that like 2 days ago, but I finally got there. So it's okay. At least we got there. So good. So at the end of last time, we started talking about induced EMFs. So again, basically, this is going to give us the connection between the electric field and the magnetic field, which we'll see eventually soon enough. But basically what we said was if we had some sort of coil, so if this was, say, my loop of wire or coil or whatever this thing is, and then we cause something to change, for example, the strength of the magnetic field. So here, if I take my bar magnet, which has magnetic field pointing downward, and let's say I move that guy then towards my loop of wire here, what that's going to do then is it's going to induce a current by inducing a magnetic field on the interior of, there we go, this coil here. So current is then going to start to move, but to get current, I have to induce an EMF, which means I have to induce a power source inside of here. So basically what we said is that the induced EMF that's created by Faraday's law is then equal to negative, where negative is Lenz's law, where Lenz's law says that the induced current or the induced magnetic field is to oppose the change of the external flux, is then equal to the number of loops times then the time rate of change of the magnetic flux. All right. So here magnetic flux is the integral of B dot dA, but here be a little bit careful that this is different from Gauss's law, because remember Gauss's law, we had the closed surface integral. So we integrated over the entire surface area of a 3-dimensional object, where for magnetic flux here, this is only a 2-dimensional object. So we're integrating over just the area of this 2-dimensional object. So it's a little bit different from Gauss's law. So it's not a 2D integral over a 3D object. This one is purely a 2D integral over a 2D object. Again, if this magnetic field is position independent or if the area is changing, something like that. So good. So again, this is just the number of flux which is penetrating through the actual area that we're going to be interested in, which in this case would be, say, the loop. Okay. So again, practicality terms, what's happening here then is we're inducing a magnetic field, which then induces an EMF, which then induces a current, because inside of this wire, I have a resistance R. So I have to have an EMF come before the current, which means that we have to have actually the magnetic field happening first. Okay. So things we didn't get to talk about, let's talk about it now. There are in general 3 ways that this can occur. So the first way is that the magnetic field itself is time dependent. So this can be one of 2 different things. So meaning that here what I'm drawing is, here's my loop. The area then is parallel to the loop, so that dot product is simply equal to 1. And let's say the magnetic field is non-spatially dependent. So as far as spatial components are concerned, this guy's constant. So my flux then is simply the magnetic field times the area. So one thing can happen, one way this can happen is if the magnetic field itself is growing. So for example, this is generated by like an electromagnet. I have currents actually running through it, which then causes the magnetic field size to get bigger over time because I'm either increasing or decreasing the current inside of my electromagnet. So basically what's happening here is that the magnetic field itself is just increasing because I'm, say, increasing more current, which causes more magnetic field strength. Okay. Or the other way is like with the bar magnet. With the bar magnet, I'm moving the magnet, which then increases the strength of the magnetic field inside the loop as a function of time, even though the actual magnetic field of the magnet doesn't ever change. But again, as the magnet is moving, the strength of the magnetic field inside of the loop is actually time dependent, because it starts off with a little bit of magnetic field in there, and as the magnet gets closer, the strength of the magnetic field increases. So this is one of 2 ways that this can actually happen, but all this says then is the magnetic field itself is time dependent, which means my induced EMF then is going to be equal to negative N times A times the time rate of change of the magnetic field. Option number 2 is the area itself is changing. Again, there are multiple ways that this can change, but the way I decided to draw it here was initially at time is equal to 0. I have the small area here. So the area again is parallel to the magnetic field. So my flux again is just B times A. But in this case, I'm grabbing the wire and I'm pulling it outward, which means that I'm changing the area from a small area here to now a much larger area, which means the area itself is actually time dependent. So in that case, the EMF is going to be minus N, which is again the number of loops times magnetic field times the time rate of change of the area. So here I just need to know how the area is actually changing with time. Or the third way is that the angle between the magnetic field and the area. So remember, the angle is specifically between the magnetic field. So this is my magnetic field. This is my area vector, say pointing off in this direction. Then the angle theta is the angle specifically between these two guys. So what could happen in this case is that the angle between the area and the magnetic field are constantly changing. So that's actually time dependent. For example, I could have a loop such as this, which is connected to two rods, which is actually rotating about the rods here with a constant angular velocity. So imagine this is my coil. My coils are simply rotating with constant angular velocity in an external magnetic field. So what that means then again is if the magnetic field is spatially constant, the area is spatially constant, then the flux in this case is then V times A times cosine of the angle between the two, which means my EMF then, I would just take the derivative of the cosine term. So the omega would come out. So this would then be equal to N times the angular frequency times the magnetic field times area times sine of the angular frequency times sine. Turns out this is actually your AC generator. So the way that most power companies actually create AC power is they simply take a loop of wire, put that into an external magnetic field and let it rotate about. And as it rotates, what that actually does is it changes and makes the EMF time dependent, actually sinusoidal, and it actually creates a sinusoidal current as well. Right? So what will happen is as it's rotating about, the current then starts switching and going in different directions because this thing is always coming in or going out of the magnetic field. So your AC generator is actually just simply a coil in an external magnetic field, which is rotating about with a constant angular velocity omega. So in the US, for example, we use a frequency for this guy to rotate about at about 60 hertz. So this is in the US. And in other places, such as Europe, they use actually 50 hertz. So in Europe, they actually rotate about at 50 hertz. So actually the power which comes out of your house, for example, is an oscillatory AC source, which is rotating about at 60 hertz. But if you went to Europe, it would actually be at 50 hertz. So hopefully we'll talk more about that later. So these is in general the three ways that this can happen. Now, mind you, it could be a combination of all three of these. I could have a time-dependent magnetic field with a time-dependent area with it rotating about with an angular velocity. So it could be a combination of all three. So it can either be one of these three, combination of any sort of these guys. So this is the way that it can actually happen. So let's do some examples. So let's talk about ways that we can actually generate EMFs. And we'll get some practice with Lenz's law and all that kind of good stuff. So let's look at this first problem. Look at the easiest one first. So this one says we have a 100 loop square coil. So basically I have 100 loops. So N in this case is equal to 100. Square coil of length side L is equal to 5 centimeters and has a total resistance of 100 ohms. The resistance is there just to make sure the current is going to run. Is positioned perpendicular to a 0.6 Tesla magnetic field. It is then quickly pulled from the field at a constant rate perpendicular to the magnetic field region, where the magnetic field abruptly goes to 0 at some spatial location. So at t is equal to 0, the right edge of the coil is at the edge of the magnetic field, and then it takes 0.1 seconds for the whole entire coil to come outside of the magnetic field region. So it goes from magnetic field region to 0 magnetic field in 0.1 seconds. So from here, we want to find the time rate of change of the magnetic flux through the coil. That's part A. Part B, we want to know the EMF and the induced currents inside of the coil. Part C, we want to know how much energy is dissipated by the coil. So meaning I have current running through a coil with resistance, so we have to give off power. So we want to know how much energy is lost in this amount of time of 0.1 seconds. And then finally, what is the average force required to move this thing at constant velocity? Okay, so we'll talk about that in just a second. So good. So this is the first example we're going to look at. So let's draw our picture. So what this is saying is I have, here is my magnetic field region. So it goes abruptly to 0 on one side. So on this side, I have magnetic field is not equal to 0. And on this side, I have magnetic field is equal to 0. And over here, we know this is 0.6 Tesla. So we know it points in some direction. So I'm going to arbitrarily say that my magnetic field is pointing towards us. So this is the direction of my magnetic field. So anywhere within this region, magnetic field is pointing towards us with a constant 0.6 Tesla. Okay. So this is all my B's. So good. So now what it says is I'm going to put a coil inside of here. So at time is equal to 0, my square coil is going to be located here. So this is my square coil where this has side length L, this has side length L, where L was equal to, how much was L again? 5 centimeters. Good. So L here is 0.05 meters. That's a 0. There we go. So good. So what's going to happen then is we want to move this thing with constant velocity in this direction. So this is my velocity V. So that's at some time later. So I have delta T, where delta T is equal to 0.1 seconds. My coil then, I'm going to draw that one in green, is now going to be completely outside of the magnetic field region. So this is now my coil here. Good. So this guy is just located outside of this region. Okay. Good. So again, this is time jump from T is equal to 0 at this location to now this point, which is T is equal to 0.1 seconds. Okay. So in this time frame, it has gone completely outside. So again, part A, what we want to know is what is the change in magnetic flux with respect to time? Oh, sorry, just the change in magnetic flux. That's part A. So part A, all we want to know is what is the change in magnetic flux going across from this location to this location. Okay. So good. So we know change by definition is always going to be equal to the final minus the initial. So this is going to be the final magnetic flux minus then initial magnetic flux. I'll hide your guys' faces for a second. So minus my initial magnetic flux. Good. Now, in this case, my area vector, remember, will point perpendicular to the surface of this coil, which means that depending on the direction at which the current is running through, my area then will either be pointing out of the page or pointing into the page. But regardless, what that means is that the area is either parallel or anti-parallel to the magnetic field, which means my dot product, my cosine term, is simply going to be equal to plus or minus 1, depending on if this guy is parallel or anti-parallel to him. Which means then that's what? My initial flux, which is coming through my coil, is then simply going to be the magnetic field times the area, which then is going to be equal to simply the magnetic field times the area, which is the entire area. So this is then times L squared. My final flux then is going to be equal to the same thing, but in this case, since it's on the exterior, the magnetic field is simply equal to 0, which means my final flux is equal to 0. So from here, what this says then is my change in magnetic flux is going to be equal to 0 minus then B times L squared, which means that my initial flux is just minus B times L squared. So this is then equal to minus 0.6 Tesla times 0.05 meters squared, which then works out to be, plug this guy in. So this is then minus 1.5 times 10 to the minus 2. And then, oh, sorry. So that's this guy. So what am I looking for here? Go back to part A. Forget what part A actually says. Oh, the rate of change in the magnetic flux. Okay, sorry. So that's the change in the magnetic flux. Sorry about that. So the question is asking for what is the rate of change in the magnetic flux? Well, the rate of change in magnetic flux is simply equal to this guy divided by the change in time. So that's going to be equal to minus B times L squared divided by delta T. Sorry about that. So this turns out to be minus 1.5 times 10 to the minus 2. Flux, as we talked about before, that has units of Webers per second. So this is then my rate of change of the magnetic flux. So this guy is simply equal to, hide your faces again. So this is, again, the 0.6 times 0.05 squared divided by delta T, where delta T is 0.1 seconds. So that works out to be negative 1.5 times 10 to the minus 2 Magnetic flux again, or any flux for that matter, has units of what's called a Weber. So this is then a Tesla meter squared, which is equal to a Weber. So that's the units of magnetic flux. And this is per second because I'm dividing by 0.1 seconds. There we go. Everyone's okay? Hopefully not too bad. No, we actually answered the correct question. Okay. Good. So part B then is saying, okay, what is the induced EMF? So let's talk about the induced EMF. So part B then says, what is the induced EMF? Well, we know the induced EMF by Ohm's or Faraday's law is equal to minus the number of coils times the time rate of change of the magnetic flux. But in this case, since it's moving with a constant velocity, which means that the rate at which the flux is changing is constant, what that means then is, if we plotted this, we would have simply a straight line. So remember, if I had a straight line, so if I plotted basically the flux versus the time, means that in this case, we would get simply a straight line. So that means the derivative of the straight line and the tangent of the straight line are the same thing. So the slope of this line versus the derivative are exactly the same, since this guy is changing with a constant rate. So this is the same thing then as minus n times the change in magnetic flux with respect to time. Okay. So in this case, we already calculated this guy. We know n is simply equal to 100. So we're going to drop that negative sign. This turns out to be 1.5 volts. So I take negative 1.5 times 10 to the minus 2, multiplied by 100, that gets 10, rid of the 10 to the minus 2. The negative sign cancels out, which means my induced EMF then is simply equal to 1.5 volts. It's okay. The induced current then, by Ohm's law, then is equal to the potential, which in this case is the induced EMF, divided by the resistance. This is simply Ohm's law. So in our case, we know that the resistance is equal to 100 ohms. So in this case, we're going to take this answer divided by 100, which means that my induced current then is going to be 1.5 times 10 to the minus 2 amps. Okay. Or that's the same thing as 15 milliamps. So this is my induced current. Part C then is asking for how much power then is, well, actually how much energy, but effectively how much power are we losing? Okay. And then from there, we want to know how much energy is happening. So what's happening is as we're pulling our wire through our systems, let's go back, what'll happen is that we're going to induce a current inside of this coil. So let's talk about the direction at which the current is going to go, because that'll be important for the next part anyways. So what's happening here is as I pull the wire through, so let me draw kind of an intermediate stage. So that intermediate stage I'm going to draw in yellow here. So if I look at an intermediate stage, so let's say here's the coil sometime in between 0 and 0.1 seconds. What happens then is that the area is getting smaller, right? So initially what happens is the effective area is the entire area of the coil itself. However, as this thing is moving through the loop, this effective area then is actually getting smaller. So this would actually be one of those situations where the area is actually getting smaller. So if I go back to my cases, this is actually case 2. So I have an area which is actually getting smaller. So since the area is getting smaller, what that means then is that the flux is decreasing. And if the flux is decreasing, Lenz's law says then I have to induce a current by inducing a magnetic field, which is opposite to the change. So in this case, since the flux is getting smaller, since the area is getting smaller, then I have to induce a magnetic field in the same direction as the external magnetic field to try to keep it constant, which means the induced magnetic field I'm going to create in this case has to be in exactly the same direction as the external magnetic field since the flux is getting smaller. If the flux was getting bigger, in that case, it would induce a magnetic field in the opposite direction as the external magnetic field. But in this case, since the area is getting smaller, the flux is getting smaller. So this guy has to induce a magnetic field in the same direction to make sure that this thing doesn't get smaller. So in that case, right-hand rule number 3 says if I put my thumb in the direction of the induced magnetic field, my fingers curl around in the direction of the current, which means my current in this case is rotating through in a counterclockwise direction. So this is my induced current. So what's happening here is I have a current running through. This thing has a resistance, which means it has to have power lost, where we know that power lost, going way back to last exam, is equal to the current squared times the resistance. From here, this is then equal to the induced current squared times the resistance, which is then equal to the EMF squared divided by the resistance. So this is my power lost. But we don't want the power lost, we want the energy lost. So remember that energy is related to power by power is equal to the time rate of change of the energy, which means in this case that the energy is then equal to the integral of the power integrated over the time. Now, in this case, since the current is constant, the resistance is constant, that means the power is also constant, which means I would pull that outside the integral. So this becomes simply equal to the power times the change in time. So this is then the energy which is being lost. So my energy loss then is equal to the power loss multiplied then simply by the time. So plug in what we just found. This is then equal to the induced EMF squared divided by the resistance times my change in time. Okay. So plug in my numbers. What I find in this case then is that the energy being lost is 2.25 times 10 to the minus 3 joules. So we lost 2.25 times 10 to the minus joules in 0.1 seconds, or that's equal to 2.25 millijoules. So not a huge amount of energy, but enough. Everybody doing okay? So far so good, hopefully. Good. Finally, the last part then wants to know, okay, what is the force necessary to move this thing through the magnetic field region with a constant velocity? So let's go back to this picture and talk what's going on. So I'm applying a velocity, moving this thing with a constant velocity so it moves through my magnetic field region. So why do I have to apply a force to this to make sure that it moves with constant velocity? So let me kind of redraw my picture here so you can kind of see a little bit better why this is necessary. Good. So let's redraw our picture. So again, this is my magnetic field region. So this is my B equal to 0.6 Tesla. This is my B is equal to 0. And again, let's draw that kind of intermediate region where my loop is here. So this is my loop. Again, this thing is moving with constant velocity in this direction. And what we just said was that the current then is flowing in this direction. Okay. So what happened then is what? In this portion of the wire and this portion of the wire, they're both going to create forces, but those forces are going to be equal and opposite, which means that the force on the top portion of the wire versus the force on the bottom portion of the wire is going to be canceled. But since there's no magnetic field region on this side, there is no force here, but there's definitely going to be a force on this side because I now have a straight wire moving in an external magnetic field, which means I have a straight wire which has a current running through it in an external magnetic field. And what we know is that this thing has to then feel a magnetic force, which is given by I times L cross B, which means in this case, since my current is going downward, magnetic field is out. So I'd have to curl my fingers that direction, which means my thumb points in the direction of the magnetic force, which means this thing has a magnetic force acting on it in this direction. So what happens is as I'm pulling my wire through, I'm going to build up a force onto this portion of the wire because it has a current running through it, which means I'm going to have to apply a force on this side to overcome this built up force. So this force is basically acting kind of like a drag force. So to make sure that this thing moves with constant velocity, if I simply pushed it and wanted it to move through this magnetic field region, what would happen is this force is going to build up. This velocity then is going to go to 0 because it's going to have an acceleration, which means this thing is going to move and then stop. It's not going to make it through the region all by itself because of this force. So what I would actually have to do then is to make sure this thing moves through this region, I would have to apply an external force to the system to overcome this magnetic force, which is causing the drag force, to make sure this thing moves through my system. Now, once it goes out through this side, I can let it go because now it's just going to move through with constant velocity because it's in an external region of magnetic field equal to 0, so there's not going to be any magnetic force. But as it's moved through the magnetic field, once it starts going into the region of 0 magnetic field, I now have to start pulling on it with an exterior force to make sure this thing moves with constant speed. So all this means then is that for part D, the net force acting on the system must be equal to 0 because I want it to move with constant speed. If I take this direction as my positive x direction, what this means then is that my exterior force minus the magnetic force then must be equal to 0, which means, write it over here, my external force must be equal to the magnetic force. From here, we know the magnetic force then is going to be equal to the current, which in this case is the induced current, times the length times the magnetic field times the sine of the angle between the two. But in this case, my current is moving downward. My magnetic field is out towards me. So what's the angle between the magnetic field and the current, or the magnetic field and the length? So what's the angle between this guy and this guy? So what do you think? What's the angle in this case? No takers? Did I confuse everybody? So in this case, since the current's moving downward, magnetic field is outward, the angle between those two is simply 90 degrees. Right? These guys are perpendicular to each other. So since they're perpendicular to each other, sine of 90 here is simply equal to 1. So all this says is that the exterior force then is the induced current times the length times the magnetic field. So let's plug all that we have in. We also know that what? The induced current is the same thing as the EMF divided by the resistance times the length times the magnetic field. So plug in our numbers, we find in this case then is this works out to be 0.045 newtons. So this is the external force required to move this guy through this region of magnetic field through to the region of no magnetic field.
What would the magnetic field be? Would it be like 0.6 or would it be 0?
Once it gets over here, it's 0. But on this side, when we use the magnetic field here, it's the 0.6. Yeah.
Okay.
So it's going to be the 0.6 Tesla, because that's going to be 0.6 because that's only affecting this small portion of the area. But this is the region where this portion of the wire is feeling the force. Sorry. So what I care about is only the force on this portion of the wire here. So that portion is at the 0.6 Tesla. That's correct. Numbers okay? So I'll take stunned silence as either yes, we're good, or no, I'm confused as hell, but I don't feel like talking. So numbers okay? Good. So let's do another example. So the next example is this one. So this one says, to make the rod in the figure below, which is this guy here, move to the right at constant speed v, you need to apply an external force onto the rod to the right. We'll talk about why you need to do that in a second. And this wants to know, what is the magnitude of that external force required? That's simply this guy. And that what external power is needed to move the rod. Okay, and we'll talk about that in just a second as well. So what's happening here is this is a U-shaped conductor. So basically this is a wire which comes through here, gets bent through a U shape, comes back out on this side. And then I'm going to put a rod on top of this. I'm going to put a rod on top of this. Since this is a metal conductor, the rod is also a metal conductor, I'm now creating a closed circuit. So now I can have current running through here where this thing has a resistance of R. So let's say the rod itself has resistance of R. So what's going to happen then is I'm going to pull this to the right and an external magnetic field, which is then going to generate an EMF inside of the bar. We'll talk about why that is in a second, which then causes current to move through this system. And then if I want to keep pulling it to the right at constant velocity, for the same reason as we just talked about, it's going to create a force back in this direction. But again, we'll talk about why that is, which means I have to apply a force on it in this direction to make sure that it moves with constant velocity. So in this case, what we're looking for then is the magnitude of the force I have to pull on it to the right to make sure that it moves. And then effectively how much power is being added to the system by this external force. So there's a lot of things in here that we want to touch upon. So good. So first things first, let's talk about why the rod actually creates an EMF. So I'm not going to worry too much about the rest of the problem, but let's just say, for example, I have a magnetic field pointing outward. Okay, so this is my magnetic field. And I'm going to put a rod inside of this magnetic field region. So here's my rod. Let's say this rod has a length L to it. So this is my rod. And I want to move this guy with, say, some sort of common velocity or constant velocity to the right. So let's think about what's actually happening inside of the rod and see where this EMF is actually coming from. So for the most part, this rod moving in an external magnetic field acts almost identical to a Hall effect. So remember what happened in the Hall effect was as the charged particles are moving in the external magnetic field, they're going to feel a force causing a charge separation. The same thing is going to be true here. Because remember, if I have a conductor, I have charged particles basically everywhere throughout this conductor. So each one of these has a charge of Q. So what will happen is as I start to move the rod, each one of these charges inside of the rod now becomes a moving charge inside an external magnetic field. So let's say each one of these are positive charges. Right? So as I start to move positive charges to the right in an external magnetic field, what will happen is they're going to feel a force. As remember from last chapter, the magnetic force on a charged particle is equal to the charge times the velocity crossed by the external magnetic field. So in this case, I put my fingers in the direction of the velocity, which is this way, curl towards the external magnetic field, which is out. So I'm going to rotate my palm this way. So in that case, what that says then is all the positive charges are going to feel a force downward, where all the negative charges are going to feel a force upward. So basically what will happen then is each one of these charged particles, the positive ones are going to feel a magnetic force downward. So as this rod is moving, let's say this thing has moved from this location to this location, what'll happen is all of these charged particles will feel a force downward. So what'll happen is I'm going to build up positive charges on this side of the rod. So this side's going to become positively charged. Meanwhile, all the negative charges are going to feel a force in the opposite direction. So this side's going to become negatively charged, which will then create an electric field on the interior. So I'm going to have an electric field which points from the positive charges to the negative charges, which also means I'm going to create a potential difference. Mm-hmm. So now I'm going to create a potential difference across here. But as I create an electric field, what will eventually happen is what? As I move this guy more, the electric field is going to get bigger and bigger and bigger, which means the charged particles which are trying to move down in this direction, the positive ones are going to feel a force upward due to the electric force, where the negative ones are going to feel a force downward due to the electric force. So what will happen then is that eventually these charged particles will stop moving because the electric force is going to equal that of the magnetic force. So eventually what will happen is that the electric force is going to equal the magnetic force, which means that Q times E then is going to be equal to Q times V times B. So the Q's are going to cancel, which means in this case then that the electric field is going to be equal to the velocity times the magnetic field. But the EMF that I create across this is simply then going to be equal to the electric field, or the electric field is equal to the EMF divided by the length of this rod. Let me call that curly L. So that's going to be equal to V times B, which means this guy's going to create an EMF, which is then the magnitude of the magnetic field times the velocity times the length of the rod. This is what's known as a motional EMF. So this EMF, which is actually created inside of the rod, is due to the fact that the rod itself is moving with a constant velocity, which again mimics basically the Hall effect. So as this thing is moving, the charged particles on the inside are going to cause a charge separation. The positive charge particles are going to move to the bottom. The negative charge particles are going to move to the top, creating an electric field, creating a potential difference, which then creates this motional EMF. So the pure fact that this guy is moving creates this EMF. And this is what we call a motional EMF. It's due to the motion of the rod itself. Now, what's happening in our problem then is we're taking this rod. So here's my rod, which has a resistance R to it. And we're going to put this over conducting rods. So here's one rod, here's another rod, which are then connected this way. Okay. And what I'm going to do is I'm going to apply or cause this thing to move at a constant velocity moving in this direction. Okay. Now, as we just talked about, what will happen then is this guy moving in an external magnetic field. Again, let's take our magnetic field pointing outward throughout the entire region. This thing is going to create an EMF across the rod, where that EMF, again, is going to be equal to simply the magnetic field times the length times the velocity. Now, since I'm creating a potential source, an EMF, that will then cause current to move through my system. So current then is going to move through the system, which means that now this thing is going to have currents running through it in an external magnetic field, which means it's now going to feel a force. So first of all, let's think about the direction of the currents running through this loop. Now what's happening here is I start off with an area this big, but then I'm going to pull my rod to the right, which means my area then is going to get bigger and bigger and bigger, which means that since the area is getting bigger, the flux then is getting bigger, which means the induced magnetic field I'm going to create is going to be in the opposite direction of the exterior magnetic field since the flux is getting bigger. So remember, Lenz's law says that the direction of the induced magnetic field will be opposite to the direction of the change. So in this case, since this one is getting bigger, this has to be in the opposite direction to try to make it constant. So right-hand rule number 3 then says, if I put my thumb in the direction of the magnetic field, my fingers are going to curl around in the direction of the induced current, which means my current then in this case is going to move in the clockwise direction. So this is then my current, which means as far as the rod is concerned, I have current then moving down through the rod. So since the rod has an induced current, which is moving through it in an external magnetic field, the force on that rod again is going to be equal to the current times the length crossed by the external magnetic field. So in this case, I put my fingers in the direction of the current, curl towards the external magnetic field. My thumb is going to point in the direction of the force. So this thing is going to have a magnetic force pulling it backwards. So again, this is going to act like a drag force. But since I want this thing to move with a constant velocity, I then have to pull it to the right with an external force, which is equal and opposite to this magnetic force. So good. By the same reasoning as before, we then have to have that for part A, the external force then is equal to the magnetic force. Our magnetic force then is going to be I times L times B, because again, I is going downward, B is out of the page, so they're at a 90-degree angle from each other again. So sine of 90 is simply equal to 1. So it's going to be equal to I induced times the length times B. Now in our case, I induced is from the fact that this thing is generating the EMF. So this is going to be the EMF divided by the resistance times the length times the external magnetic field. But this EMF is motional EMF, and we just found that the motional EMF is equal to B times L times V. So if I plug that in, this then becomes B squared L squared times the velocity divided by the resistance. Okay, so this is the external force required to move this thing at constant velocity. Is everyone okay with this? Scrolling through and looking at faces, trying to see how many confused faces I can find. Most of you don't have your cameras on. You're making me sad. Okay. Everyone okay? Don't lie to me. I tell that to my kids all the time. Okay. Everybody's doing okay? So good. So this is then the force, right? So the next part of the problem says, okay, well, if I'm applying a force to this thing, that means I am also applying an external power. So what that means then is that for part B, the external power then is equal to the external force dotted by the velocity. Okay? So remember that the definition of power, the other definition, is that it's the force dotted by the velocity. Now if we go back to our picture, what's happening here is my force is in exactly the same direction as the velocity, which means those guys are parallel to each other. So I get a cosine of 0 degrees, which is simply equal to 1, which means this is the same thing then as the external force times the velocity, which now is equal to B squared L squared V squared over the resistance. So this is the power the external source is applying to the system as it moves it at a constant velocity. Okay. Now, just to illustrate something, if this is what's being supplied by the external force, what is the power being lost by the resistor? So how much power is being lost by the resistor? Well, we know the power being lost by the resistor is equal to what? The potential squared divided by the resistance, where the potential squared is equal to what? The EMF squared divided by the resistance. The EMF we know is equal to B times L times V squared divided by the resistance, which is then equal to B squared L squared V squared divided by the resistance. So just to kind of illustrate something, what's happening is as current is running through my system, the resistor, or in this case, the rod, since it has a resistance, is losing energy due to the fact that it's moving in an external magnetic field. And it's losing energy at the rate of the magnetic field squared times length squared times velocity squared divided by the resistance. But to move it at a constant velocity, I have to apply a force to it, where I'm then applying a force, which means that I'm adding energy to the system, and I'm adding energy to the system at a rate of the magnetic field squared times the length squared times the velocity squared divided by the resistance. So what's happening then is the resistor is losing energy at the same rate that I am putting energy into the system. Now, my overall question is, does that make sense? Does it make sense that if my system itself is losing energy at a rate of B squared L squared V squared divided by R squared, and I am putting energy into the system to replace that energy? Right? So I'm putting in energy at the same rate that this thing is losing energy by itself. So again, the question is, does that make sense? Does that seem like something that is reasonable or not? So this is what I want to know. Does this make sense? And why? So, what do we think?
Did you want like a word answer?
I want a word answer. Yes. Not a mathematical one that these things are exactly the same, but I want a word answer. So why does this make sense that the power that I'm adding to the system is exactly the same as the power that the system is losing?
Because the energy can't be created or destroyed, so you're just having a change of energy, and the total change will equal zero.
Exactly. So this is just conservation of energy. Exactly. This makes perfect sense by conservation of energy. So what's happening again is I'm moving this rod with a constant velocity, which means the kinetic energy at which it starts off is exactly the same as when it finishes. So as this thing is moving through, I'm not changing the energy, which means that if the rod itself is losing energy due to the fact that it's radiating away due to thermal energy, well, I have to add in that same amount of energy to make sure that conservation of energy exists, right? So as long as this thing moves with constant velocity, the change in kinetic energy must be equal to zero, which means that my change in total energy is equal to zero, because I'm also not changing the potential energy, which means that, yes, these two things have to be the same based off of conservation of energy. Whatever energy I lose, I have to replace to make sure that my change in energy is zero. Exactly. That's right, Dirk. Good. So let's do another example. Let's do some calculus. That'll be fun. So my last example I have for you, so these are all basically motional EMF questions. So this one says we have a rod of length L equal to 10 centimeters, so that's this rod down here, is forced to move at a constant velocity to the left, in this case, 5 meters per second, along these horizontal rails. So these are my horizontal rails. Again, this thing has a resistance R in it, and I'm causing this thing to move with a constant velocity of V. Okay. Then it says the rod, the rails, and connecting strip at the right form a conducting loop. So as this thing is moving, I'm gonna have a conducting loop through here, which just makes sure that I have current running through the whole thing. So it says the rod has a resistance of 0.4 ohms. The rest of the loop has negligible resistance, which means we're gonna pretend everything else is zero resistance. Then it says a current, 100 amps runs through this straight wire here. So this is a straight wire, which has 100 amps worth of currents running through it at a distance of 10 millimeters from the loop, which then sets up a non-uniform magnetic field. So basically what that means is this side of the loop here is 10 centimeters away from the wire, which means that this side here is then going to be what? 10 centimeters with 10 meters, right? So that's on this side over here. So that's going to be what, 1.1 centimeters then. So here it wants us to first find the EMF and then find the induced current. It should be, yeah, current induced in the loop. And then I want to know at what rate is thermal energy being generated? What is the magnetic field to make sure that this thing is moving at constant speed? And then finally, at what rate does these form, that should be force. There we go. What rate does the force do work on the rod? Okay, so good. So let's draw our picture here. So basically the same picture as before. So here is my wire. So here's my wire. This is what's going to be generating the external magnetic field. So here we know this thing has a current running through it in this direction, I, which is equal to 100 amps. Okay. Then down here, we have our conducting rods. That's connected over here. And then we have our rod moving across here. So here is our rod. Great. Which then is moving to the left with a velocity v equal to 5 meters per second. Okay. And we know that the length of this rod here, so I'm going to call that little l, is equal to 10 centimeters. And again, we know this distance gap here is a, which is equal to 10 millimeters. Okay. So good. I think that's all the information we need. Why is my pen not working? There we go. Good. So part A is we want to know what is the induced EMF inside of the wire, or the induced EMF inside of this guy. Now, the problem here is if we simply said this was equal to B times L times V, like we did in the last problem, because this is a motional EMF inside an external magnetic field, this would actually be incorrect in this case. And the reason it's incorrect was, if we go back to our picture back here, we're assuming that the magnetic field is equal to a constant, which means that the magnetic field down here is the same as the magnetic field up here, which means that we didn't have to do an integral. But in this case here, what's happening is the magnetic field here is much greater than the magnetic field down here, because the magnetic field is being generated by this wire. So in this case, if we simply wrote this down, this wouldn't actually be correct in this case, but we would have to actually do the integral when it comes to the flux. So for this one, the first thing we're going to actually have to look at is what is the magnetic flux through this portion of wire here. Okay, so what is my magnetic flux? So we know this is equal to the magnetic field dotted by the differential area. So good. So first things first, let's talk about the direction of the magnetic field. So again, we know this guy's creating a magnetic field. Right-hand rule number one is we put our thumb in the direction of the current. Our fingers would curl around in the direction of the external magnetic field, which means in this case, our magnetic field is going to curl around in this direction, which means anywhere down here, the magnetic field is coming out of the page. So my magnetic field is going to point this way. So this is my B. So here, we're going to go ahead and take the fact that our area points out in the same direction, so that here, this is going to become simply equal to the integral of the magnetic field integrated over the differential area. Now, since the magnetic field is created by a wire, we know the magnetic field of the wire is equal to mu naught I divided by 2 pi r. Okay. So our magnetic field in this case is spatially dependent. Now, what's our differential area? So in this case, our differential area is going to be a little tiny section here. This is my differential area dA, right, which is going to point out towards us. Oops. Go away. I'm almost out of time. So let's just kind of set up this integral and we'll go from there. So good. So dA is going to be then, so basically again, here is my dA. So dA is a small section in this direction, but this direction is what? The radial direction, which means dA in this direction is simply dr, and dA in this direction, I'm going to go ahead and call going this way the x direction. So that means dA in this direction is going to be dx. So all I'm doing is I'm drawing out this little area here, where this little area has a length in this direction of dr and a length in this direction of dx. Okay. Which means my differential area then, this entire area, dA, is then going to be equal to dx dr. Okay. Okay? Now, since a magnetic field only depends on R, that means X I don't really have to write as dx, because I can do instead a very long strip, which overall has a length of X to it, and then still has a small area here of dr, which means my overall differential area is going to be simply X times dr. And that's because the magnetic field doesn't depend on X. So let's plug that in. So this is finally going to become equal to the integral of B, which is mu naught I over 2 pi r, times my differential area, which is X dr. Now here, I'm going to integrate from this side of the connecting rod to this side of the connecting rod. So I'm going to integrate from A to L plus A. Now everything here is a constant except for the dr and the r. So this is going to become equal to mu naught I X divided by 2 pi integral from A to L plus A, then dr over r. Well, what's the integral of dr over r?
Natural log.
Natural log, good. So finally, what I get then is what? My magnetic flux is then going to be equal to mu naught I X divided by 2 pi natural log of R evaluated from A to L plus A. So this is then just going to be what? Mu naught I X divided by 2 pi times then the natural log of L plus A divided by A. So this is my EMF, or sorry, this is my flux. To get my EMF then is magnitude-wise equal to N, which is 1 in this case, times the derivative with respect to time of the magnetic flux. Now, as my rod is moving to the right, the only thing which is changing is then the length of X here, which means as this thing moves from this location, so if this is initially X, to now this location here, my X is now going to change, which means X is the only thing which is actually time dependent in this case. So when I take the derivative of this, mu naught I, 2 pi, L, A are all constants. So the only thing which is actually time dependent is simply X. So this is going to be the same thing as mu naught I divided by 2 pi natural log of L plus A divided by A times dx dt. Well, what's dx dt by definition? So what's the time rate of change of position? What do we call that?
Velocity.
Velocity. So finally, this is then just mu naught I over 2 pi times the velocity times n ln of L plus A divided by A. Okay. This is then my induced EMF. The rest of this we'll have to do on Monday. Just to get us started. But this is the magnitude then of the induced EMF inside of this rod. Okay. So, any questions up to this point? Now again, here the integral is necessary again because the magnetic field is non-constant. If it was constant here, then we would just use this guy. That's it. But in this case, since it's non-constant, we have to integrate over the actual differential area, which means it's going to be a slightly more complicated, but not too bad.
So is it just not constant because one side's closer than the other one?
Correct. Correct. Now it would be different. So I'll make it a little bit of elaboration on that. So it would be different if my wire was doing this and my rod was moving this way. So if my rod was moving this way, so if my conducting rods were like this, then anywhere along the rod, then the magnetic field is simply constant. That's right. So if it was moved so that the rod itself was parallel to the magnetic field, then in that case, yeah, I wouldn't have to actually do that integral. Exactly. But in this case, since we have it so it's moving, so the rod itself is perpendicular to the wire, then in that case, that's what makes it non-constant. That's right, because it's bigger on this side than it is on this side. Exactly. Exactly. Good. So, are we doing okay so far? We'll talk about the direction of the induced EMF and all that good stuff on Monday. And just to throw that out there, that was a few years ago, actually an exam question, but I don't ask them that hard anymore. So not to scare you, but just to let you know, that was an exam question at one point. So good. So everybody okay? Any questions? Doing good. All right, so I will see you all in person on Monday. It'll be great. I haven't seen you guys in forever. Okay, so have a good day. I'll see everybody. Have a good weekend. Don't forget, 1 week from today is the exam. Bye. Everyone.